Oh, by the way, just if anybody has some questions, yeah, just please send me you can just send your question to me on the chat room. Okay, yeah, on the view the chat, so I will forward the question to Dr. Wu. Yeah. I think Dr. Wu, I think we are. I think we have how many people now? We have 20. Yeah, I think we can consider starting now.
Okay. Good morning, everybody. Thank you for joining this meeting for this presentation. So today I would like to present a project Dr. Liang and I have working on also several years. So the project is about monitoring, mapping urban underground infrastructure. So before I introduce the project techniques, so first I want to give credit to our students, Maxwell, Will, Evan, and Simon, and also faculty member Dr. Liang and me. So this is a collaborative project with the University of Vermont, Dr. Driver Houston and Dr. Tianxia. Okay, so first I will briefly introduce the background and motivation for this project, the goal and vision of the project. Then, so I will focus on one type of subsurface sensing device called a ground penetrating radar. So we proposed cognitive GPR. So I will introduce the major technique as computing and reinforcement learning for this cognitive system. And then lastly, I will briefly introduce the urban infrastructure mapping research we did. Okay, so for the background motivation, we know right now smart city research is a very hot topic. So smart city not just about infrastructure, transportation, right? Smart energy, smart house above ground. Also, underground utility is a critical part of this smart city research area. We know underground utility is very critical, but in the US underground utility are not very good. So for example, in 2017, the ASCE gave D to US drinking water infrastructure and D+ to wastewater infrastructure. So this is not very good. So basically, these infrastructure, they have unknown locations, especially in old cities. And also they have congested configurations. You have different, for example, pipelines, cable pipelines, drinking water pipelines, gas pipeline. Also, their conditions are unknown or aging. So they definitely need some, advanced technique to have a good understanding of their conditions and locations. So bad conditions of underground infrastructure, for example, pipeline leaks, so they could cause serious problem. They cause, for example, economic loss, health issues, and for example, safety issues caused by gas pipeline exploding. And also, water pipe leak can destroy, for example, streets. So based on this observation, the goal of this project is set to, okay, so we use different sensors, including underground sensors. For example, this underground in-pipe robot carrying some, for example, acoustic sensor to detect leaks, and also above ground sensor, like we will introduce ground penetrating radar. We collect the data about underground infrastructure, basically pipelines. So those data transmitted to, for example, high performance computing computer, and then we do modeling and data analytics. Ideally, we could have a live information system. For example, people like infrastructure workers, so they can check the condition and location of underground infrastructure anytime by using portable device. Imagine, for example, utility worker, for example, working on the street. As long as they take a picture of the street, they upload the picture of the street to our server. So our server should be able to push this kind of information, for example, in the form of like with virtual reality or augmented reality. So push the information to their device, so they can check, for example, the condition and the location. These are the information from the will be showed on the device. So with this kind of live information system, you can imagine is very important for many aspects of a smart city. It will be very useful for utility business to maintain their pipelines. It's also useful for construction companies like DigSafe, right? Also city planning, emergency response, first responders. Okay, so let's here we mainly carried on the research on a subsurface sensing device called ground penetrating radar. So here you can see this is the working mechanism of ground penetrating radar. Basically, a GPR, it has a pair of transmitting and receiving antenna. The transmitting antenna emits some radio wave, electromagnetic wave into the soil. So when the radio wave hits an object, which could be a pipeline, the radio wave will be reflected above ground. The receiving antenna will capture the radio wave. So you can see from the animated figure in the right, so you can see, so this is the radio wave propagating in the soil and reflected by the object represented by the circle. So basically, here we have different types of GPR data. We have called it A scan, B scan, even C scan. So what is A scan? A scan is a one-dimension GPR data. So imagine here, like we have, for example, a pipe, metal pipe or plastic pipe, right, buried in the soil. So above ground, you move a GPR. So when the GPR, for example, at a position here, so the GPR, okay, sends some radio signal into the soil. So the radio signal will be reflected by the pipe, captured by the receiving antenna. So you can see this is the path of the radio wave. So if you plot a circle with this radius, I don't know, can you see my mouse? So it shows the path. If you plot a circle, so this length goes to the vertical direction. This length actually is you can see it is the travel length or the travel time of the radio wave, right? So when the GPR moves to a different position, it will be send another radio wave, another trace of a radio wave, so reflected. So this will be the travel time of the radio wave. So if you do this multiple traces, so you will have, for example, you have multiple A scan. So each trace of a radio wave is called A scan. So it's a one dimension. If you compose multiple A scans, it will be a B scan. Basically, it's an image. So you can see you have a hyperbola, which is similar to the hyperbola on the left. So this is a GPR B scan image. So for this image, you can see on the horizontal axis, you have a trace number, right? From 0 to 180, so corresponding the different position of the GPR. So on the most left, you have a trace 0. So when the GPR is at the right top of the pipe, so the trace number is 90, and then you have 180. For the vertical axis, it's the travel time. So you can see here, there's this is an interface like. So basically, this is the interface between air and soil. So when we send a radio wave, so part of the radio wave will be reflected by this interface between air and soil. So that's why we can also get this interface image. Okay, so we mainly focus on A scan and B scan. Of course, you can imagine you can also have a multiple parallel B scan. So if you put a multiple parallel B scan together, so it will be called a C scan. So we can see GPR basically is a non-destructive, right? So it just sends radio wave above ground, detect the received radio wave. So it can work in a variety of media. For example, can work for soil, ice, concrete. It can detect objects, voids, cracks. It has been applied in many applications, military, civil. For example, check the bridge deck, right? So you can see from the left figure, there could be some noise interference. So you can see the soil has multiple layers, right? So imagine this radio wave, when it hits to the interface between different soil layers, you will receive the GPR will receive some reflected radio wave. So that you can see there's some noise or artifact in the B scan image. Another thing is GPR has many operating parameters to adjust to get the best scan performance. So here we have 3 rebar. You can see the antenna of the GPR could be put a different direction. It could be put perpendicular with to the rebar. Could be put parallel with rebar, or 45 degrees to rebar. So these are the different B scans for different arrangement of GPR antenna. So apparently we can see it seems the GPR, the B scan image with antenna perpendicular to rebar is the best, right? We can get very clear hyperbola. So for parallel arrangement of antenna, so we almost got nothing. So here you can see the alignment arrangement antenna. The angle of antenna is an operating parameter, so we can adjust. Another parameter, I just give you an example, is the operational frequency, radio frequency. So we can have a GPR, for example, using a frequency 400 megahertz, 1.6 gigahertz. So we know for low frequency radio wave, it has a high penetrating capability. So for example, here we have a pipe, the bearing depth is about 75 inches. So if we use 400 megahertz frequency, so we can get this kind of GPR B scan with some hyperbola trace. But if we use 1.6 gigahertz, we cannot get anything. So this is another parameter can adjust. There's some other parameter, for example, operating power, we can adjust. So basically, I want to see, okay, we have some operating parameters of GPR we can adjust to get the best scanning performance. Okay, so let's take a look at how the operational, the conventional GPR operation is like. So conventional GPR operation highly depend on experience. So the expert, sets the operational parameter, for example, frequency or transmitting power, and then it scan. You get some GPR signal. So most of the time you do the offline GPR data processing, and you check the result, and then so the expert goes back to adjust the parameter. So it's a very time-consuming process. So this is some experiment. We use a conventional GPR on UTC campus. So you can see the operation is very inconvenient. This Dr. Liang so carries a power generator. Also, we need to do like traffic control, traffic management. So of course, the expert, when the expert operates the GPR, he or she can adjust some parameter. It depends on how flexible the GPR device, whether the parameter can be adjusted, online on the fly. We know there's some pipe under the East Field Street. So you can see this is the East scan GPR signal. Okay, so based on observation of conventional GPR operation, so we propose autonomous cognitive GPR. So basically, this autonomous cognitive GPR is based on two major techniques: reinforcement learning and edge computing. Reinforcement learning is used to generate intelligence for adaptive control of the GPR, basically the control command. So for example, how much parameters should be adjusted. Edge computing brings computations, storage resources, and service to any devices. This is mainly for real-time operation of GPR. So the reason here we don't use the traditional cloud computing for this cognitive GPR system, because the long latency of this round trip. So you collect the data in the field in real time, so the data will be transmitted to the edge server. So the edge server do the data analytics, and then so the edge server will generate some control command fed back to the GPR. So if we use remote cloud, so this long distance path, so it causes much latency. So it's not suitable for real-time operation of GPR. So of course, also the user device can be connected to the edge server through Wi-Fi, can check, for example, the GPR data, check the operation of GPR in real time. So this cognitive GPR not only suitable for example, for this UAV mounted GPR, it also suitable for other, for example, wheel-based robotic GPR and handheld GPR. So it's a generic system diagram. Okay, so our goal is to develop an autonomous adaptive cognitive GPR. This is the logic of the operation of this GPR system. So the GPR scanning in the field, it collects the GPR data in the form of B-scan images. So the B-scan image sent to the edge server. The edge server does data analytics and generate control command to the GPR. The GPR will be adjusted on the fly. So also when we human in the loop here, the system, people talk about human in the loop. So again, people can use the device, for example, check, even modify the control command to the GPR. So another aspect of edge computing is we know each edge server, it has a transmitter. So, but the edge server usually the transmitter has limited coverage. So for example, usually this kind of transmitter could be Wi-Fi, could be a cellular station. So it has limited coverage. So if this autonomous GPR, flying out of the coverage of this edge server, but it fly into the coverage of another edge server. So in this scenario, we need to do migration, called service migration. So basically, the service on this edge computing server will migrate it to the available edge server for the GPR, so that the operation of GPR, the autonomous process of GPR operation can be continuous. Okay, so this is yeah. So here, this is the architecture of the proposed cognitive GPR. So this is a closed loop system. So you can see on the left side, basically this is the GPR front end we call. So you have a GPR mounted on a drone or some other robotic platform. So this GPR front end has onboard computer. So the onboard computer can do some, real-time data pre-processing. Of course, you have a GPR transceiver, transmit and receiving antenna. So the captured data will be sent to the GPR backend, which is the edge server. So at the edge server, we do signal processing. So GPR signal processing, data mining, and also on the server, we could have some GIS database, right? For example, the pre-copied location of the pipe. Just some, preliminary information. It could not be exact. If we have exact information about underground pipeline, we don't need to use GPR to scan the field. So we want to combine this GIS information to generate more accurate control command. The control command is generated by this cognitive analyzer. So this is the smart part of this system. So the control command will be fed back to the GPR. So the GPR can be adjusted. So here you can see the GPR operation. Conventional GPR usually do this kind of grid-based scanning. So you do this parallel line-by-line scan. So of course, with this autonomous control, we can also do freeform scan. Also, this autonomous GPR can be integrated with other sensors, for example, cameras, a GPS sensor, to get more information about the field. So all this information could be transmitted to the edge server. So for data analysis. So this is a adaptive system, a real-time system. Okay, so continue with edge computing part. So I will first introduce edge computing and then so introduce the reinforcement learning technique. So because the computation could be very intensive, so we need to identify some computation task involved in the operation of GPR. So here you can see this is the raw GPR data. You could need to do some signal denoising. So this could be some computation task, just to filter out the noise. This can be considered step one. And then step two, you do time zero correction, right? So we just want to remove this, like a hair card, remove this interface caused by the interface between air and soil. Also, we need to do like a signal enhancement to enhance the contrast of the signal. The contrast with the hyperbola curve. Another step, so we may need to identify a region of interest. So this area, the hyperbola, is our interest, our focus. So next step, so after we identify region of interest, we could use, for example, deep learning network, for example, convolutional neural network, and do further the feature extraction, try to, for example, classify or predict some predict the corresponding underground object. So we can, for example, classify, for example, we can determine pipeline material, pipeline diameter, barrel depth. So this information about the underground object. So this is a typical convolutional neural network diagram. So you have this different layers, some sampling convolutional layer. So you have a fully connected layer. So the final output will be the predicted result. For example, okay, it is if we want to classify, for example, the pipeline material, so the result would be like, okay, it is a plastic pipe. If you want to classify the barrel depth, so it will tell you, okay, so the barrel depth is, for example, 1 meter deep. So once we identify different computation tasks, we need to determine, right? Remember, we have an onboard computer as the front end of the GPR. Also, we have a back end at the server, so we can determine which computation task should be executed at the front end, or should be offloaded to the edge server. So how to determine this? So we know, I mean, different computation tasks, they have different input data, output data, right? So the input data and output data, they have different data size. So we need to consider, you know, the transmission latency and the computation latency for each computation. We need to evaluate the latency if it is executed locally, which is at the front end of GPR front end. We also need to evaluate those latency if it is offloaded to the edge server. Because another thing is because you know, mobile robotic GPR platform, they are mobile, so they have a limited energy resource. So if we want to minimize this energy consumption of the GPR front end, so we may need to take into account the you know, the energy consumption. So this algorithm about is, okay, for each computation task, we evaluate, you know, the latency here, the T. We also evaluate the energy consumption for each computing task. So we do this comparison, and so we determine, okay, whether the computation task should be executed locally or offloaded to the edge server. I will not go into the detail of this algorithm. Just this is some you know, typical offloading algorithm for edge computing. So we did some field experiments with this edge computing edge server. So we use street Wi-Fi, so the transmit data through the street Wi-Fi to an edge server. So edge server is deployed in a building called a Sim Center on UTC campus. So we use this Intel mini PC acting as edge server. So this is some scanning result of the MRK Boulevard. You can see here we have some hyperbolas in the B-scan image corresponding to some pipes under the street. So this is the sewer pipe. We have this kind of GPR B-scan image. Also the transmission time of, you know, through the street Wi-Fi. So here the blue bar represents the data size. right? So you have a bunch of A-scan signals. So depending on the scanning time, so the data size could be different. So here the origin line is the transmission time. So you can see here, the transmission time is not proportional to the data size. So sometimes even the data size is small, but the transmission time, transmission latency is large. This is mainly due to the unstable transmission rate of the street Wi-Fi. So this is different from a simulation. With the simulation, if we don't add fluctuation of the Wi-Fi transmission rate, so the transmission latency is proportional to the data size. So in real world experiment, so we have a little bit different result. This is the real world result about the transmission latency. But whatever the data size, B-scan generation time, pre-processing time pretty similar. You can see represented by different by a gray color and yellow color. So these operations they have pretty similar latency regarding the difference the GPR data. Okay, so that is about the edge computing, one of the major technique for this cognitive GPR. So another technique is reinforcement learning. So we try to generate intelligence for autonomous control of the GPR. So reinforcement learning mainly solve a type of problem where an agent interacting with the environment. So the agent and the environment, we can define different states, right? So the state could be, for example, the state of the environment or the position of the agent in the environment. So for example, at a state, so if the region take an action AT, so okay, the environment will yield some reward to the agent. The agent will get some reward, and then it will go to the next state. So and then so it continue with another action. It get another action, another reward, R T+1. So this is a pretty sequential process. So for example, here this is an example. Let's see this this agent could be a dinosaur. The dinosaur in for example botanic maze, trying to find some its favorite food plant. But the dinosaur does not know the exact location of this plant. So it can only, do this kind of exploration of the maze. So, when the dinosaur searches for the plant, it could get some reward. So let's assume, for example, the reward could be some, scent from the plant, right? So when the dinosaur approaches to the plant, it will get, for example, strong scent, strong smell of the plant. So based on the strength of the scent, so the dinosaur could be, get the plant. So the dinosaur could have different actions in the maze, right? For example, turn right, turn left. The states could be defined, for example, what is the position of the dinosaur. Okay, so So right now the maze does not change. If the maze also changes, so the state should be able to reflect, you know, the change of the environment. So that is the part of the state definition. So when the dinosaur, you know, do one action, does one action, so it will, for example, move one step, it will sniff the air, sniff the strength of the scent, which is the reward it will get. And then, so based on the reward, it will try the next action. So this is an iterative process, which is, you know, a sequential decision-making process. So how to make optimal actions? How to have you know, optimal sequence of actions? A typical algorithm for this kind of you know, sequential decision problem is called Q-learning. So Q-learning is a model-free reinforcement learning algorithm. The reason we call it model-free because so in this environment, you could have different, you know, so from a step from a state to another state. If you want to model this system, for example, what is the state transition probability, right? So let's say the dinosaur at this position, it could be go upper or could go to the bottom. So what is the probability of taking either action? So this will give the transition probability. So if you want to model this system strictly, you need to have this transition probability. But in problem like this, or in our, for example, GPR, cognitive GPR, autonomous GPR system, it's very difficult to have a, you know, strict model of the system transition probability. Also, you know, the number of states is too large, so we cannot have all those probabilities available. So that's why people you know, come up with this kind of model-free reinforcement learning. So we don't need to care about the transition between states. Okay, so in this Q-learning, basically it defines a Q value for each pair of a state and action. So basically this Q value is the expected maximum total reward, I mean, yielded from being at state S and performing action A. So here we call it expected a total reward. So that is that the total reward counted from the reward you know, obtained from the current state, next state, and also all the future states. So okay, future states could be discounted when we evaluate this expected total reward. So it could be discounted. So that's why here we use gamma for this as this discounting factor. So here this Q value. So for each pair of state and action, this Q value actually is a you know, is a quality, you know, is a quantity characterizing the quality of being at state S and performing action A, right? That's why we call it a value. So value of the pair state and action. So we have this Q value for each pair state and action, And also we use this strategy. So imagine at this state, so the Q value just you know, it is receive a reward, and also this Q value also just depend on the Q value, the maximum Q value of its next state. This is called Bellman equation. So I will say this. So you can see here, we just so this Q value can be for state S and action A can be written as this: the sum of the reward for the current action, and then so the Q value for the next state. So for the next state, you could have different action to perform. So we just choose the Q value corresponding the maximum Q value corresponding to the action we could perform, right? So okay, so we use this strategy to update the Q value. So the update is a recursive process. So you can see here. Okay, so here this is a sequential process. So at time t, of course, I mean, at the beginning we can initialize all the Q values, with arbitrary value. We could initialize them with all zero, right? Then so at some time t, so we have the current value, we call the old value of this Q value for this pair ST and AT. And also, so we perform action AT, so we get this reward RT. And then, so we use this RT, we add this RT to the maximum Q value of the next state, ST plus 1. So the next state comes from the current state and with action AT. So this sum is called the target Q value. So this is like some, with the new reward. The new reward can be considered as like some observation of the environment. So with this new reward, so, this is like some update of this. I would say kind of update the current Q value, right? So this is the old value. So you can see for this difference, the difference between target Q value and the current Q value, this is like a temporal difference, right? So this is at the current timestamp t, and then you go to the next. The GPR agent, the agent reinforcement learning agent performs action AT, so it goes to next state. So we have a temporal difference. So this temporal difference will be added to the current Q value for this pair of ST AT to update the old Q value into the new Q value. So here we add this learning rate. So we want to add a weight, how much we want to utilize this temporal difference. So with this recursive update, you can imagine. So the key value for different pairs will be updated, continuously. So all the key values will be updated. Of course, depending on how much update, how much adjustment, depending on this temporal difference, depending on the learning rate. So with enough, temporal steps, so you will have, the old value will pretty close to the new value. The old Q value pretty close to the new Q value. So the Q values for each pair of state action becomes stable, becomes stationary. So you have a table of the stable Q values. So this table of Q value will be like a cheat sheet, right? So okay, so we can use this cheat sheet so for the agent. So whenever, for example, the agent, the dinosaur is at a state st doing so we check, okay, which action could bring the maximum value, and then we choose that action for the agent. So that will be the action the agent to perform to achieve the maximum value. So this is probably the process of Q learning. So go back to our cognitive GPR system. So we also have this sequential process. So at each time step, right, we can capture some GPR data, which can be here considered as a GPR baseline image. So based on this GPR image, so this is like the observation of the environment. So from this GPR image, we calculate some reward for this GPR agent. So based on the reward, so the GPR agent need to determine the action for the GPR. So this is a sequential decision making problem. Okay, so you can see from here, one challenging problem is how to identify proper reward or reward function for this GPR agent. So in our case, we want the GPR not only just does the object detection, but also do the object recognition. So this reward function for GPR agent should be able to characterize the knowledge about the subsurface object newly acquired by this GPR agent. So this knowledge of subsurface object, not only about, for example, okay, whether an object is detected or not, also including knowledge, some more, detailed knowledge about, okay, for example, what is the object of what is the material of the object? What is the diameter of the object? So this kind of a recognition of the object. So we want the reward function for the GPR agent have two parts. The first part comes from the object detection. The second part come from object recognition. So we want to combine the two parts of the rewards as an overall reward for the GPR agent. So in the other words, whenever the GPR agent detects an object, we will get some reward RI. Okay, so based on object detection, if the GPR agent can recognize the object, it can get some further information about the object, so it can get another reward. We call here we use RM. So we combine these two parts of the reward for the overall reward. So first, we try to define the reward for object detection. So here we use a region of interest to represent, okay, the object being detected. So here you can see this is a B-scan image. If the GPR agent can identify this region of interest, so we think, okay, the GPR agent detects something because it identifies some region of interest. So that means something is here, right? Produce this region of interest. So we consider that as okay, object being detected. So how to identify region of interest? So we use some existing method. We use the entropy, right? The entropy basically, captures the singularity of the captured GPR data. So lower the entropy, means higher data singularity. So you can see here, we calculated the entropy with respect to scan axis. Remember, in a GPR B-scan image, the horizontal axis is scan axis. Vertical axis is the travel time. So we calculate the entropy with respect to scan axis with respect to two-way time. So let's say here you can see in this the entropy for scan axis, right? So we compare the entropy, the blue curve, with some threshold. So if the entropy is lower than some threshold, so that means this area, so is singular. So we map the boundary points S1, S2 corresponding here the scan axis value. So for example, this is like 180 mapped to the B-scan image. So this one is like 350. So we have this boundary horizontal boundary for in the GPR B-scan. So similarly, we can calculate the entropy for travel time. So we compare the entropy with threshold. So we get this boundary value. So we map these boundary points to the B-scan image, so we get this travel time. So you can see this is like 25, so here 25, so 170. So with these four boundary points, so we can identify a region of interest. So this computation can be totally, performed by GPR agent. So as long as it has received a B-scan image, so it can calculate these boundary points, identify region of interest. So based on these boundary points, we can definitely, calculate the reward, the first part of the reward for detecting an object. Okay, remember, we also want to reward the agent for recognizing the object. So once the region of interest is identified, so this region of interest is passed to, for example, like a convolutional neural network right? So the convolutional neural network will give some classification results. So let's say, for example, we do the classification for the pipe material. So it give a vector of probability. Probability for being plastic, probability for being concrete, or metallic. So we can use this output probability vector. We calculate another entropy called standard entropy. So we know entropy is a measure of uncertainty, diversity, singularity, right? So we calculate the standard entropy with these probabilities. So we use this probability to derive the reward for recognizing the object. So we know, from standard entropy, we know, a balanced predicted probability distribution indicates high uncertainty, right? Like for, if all these probability here we have 3 probabilities. So if they are equal to each other, 1/3, so you have a high level uncertainty. We don't know which material the pipe is. So for this balanced probability distribution, it has a high entropy. So if we have a skewed predicted probability distribution, it corresponding, low uncertainty, low entropy. So for example, we have a very high value of this probability P1, so that we are pretty sure the pipe is plastic. So we use this entropy to derive or to quantify the reward for object recognition. So we have almost defined the reward for GPR agent. Okay, another thing is how to determine the actions. The Q-learning algorithm we just introduced, is not suitable for this GPR agent, because you can imagine in the real world scenario, the state space means in our case will be here. Okay, the state space will be, for example, at least you need to define, for example, the position of the GPR agent in the field, right? So in real world scenario, the number of states could be very large, especially if you have a very fine granularity about this spatial space, discretization of the space. So we have a very large number of states. Also, action space could be large. So action not just, for example, is about not just about okay, the GPR agent moving right, left. Also, but if you consider adjusting of GPR operational parameter as a part of action, for example, whether I should increase the radio frequency or decrease radio frequency, whether should increase the radio transmission power, or whether we should adjust the orientation of the antenna, how much we should adjust those parameters. So that could also be considered part of the action space. So you can imagine this space, action space are large. So Q-learning algorithms, we know Q-learning will give this kind of a Q table. So if we have a large state action space, so there will be many rows in this table, huge size of the table. So that's why we consider, okay, we use deep Q-learning. This is a very popular research area. So basically, okay, we don't want to determine this explicit Q table. So we use a neural network. Basically, I mean, this is the idea of deep Q learning. So we use a neural network to approximate the Q value. So you can imagine with deep Q learning, we don't have to have a Q table, right? So we just give a state as input to a neural network. So it will produce Q values. It will produce Q values corresponding to different actions. So the thing is, okay, of course, I mean, for this deep Q network, neural network, so it will involve some computation to calculate Q value. So remember the cognitive analyzer, the module in the back end of the cognitive GPR. So it is mainly used to generate the intelligence to control the GPR. So we use the deep Q learning to implement this cognitive analyzer. This is this is the diagram of this DQN here. So at some state, the GPR agent performs some action A, right? So perform action A, it will scan, it gets some B scan image. The B scan image will first to derive the region of interest, so based on the entropy. So in this process, we can derive a reward. We call it a reward for object detection. We call it RI reward. And then, so the identified region of interest is passed to a neural network, like a convolutional neural network. So it will do the classification. So for further, recognition of the object. So we can get the second part of reward. So the rewards are combined. The overall reward, together with the state, right? So we can have the state, we can have the action. So together the state, action, and also the next state. So the state here could be simply, for example, the position of the GPR agent in the field. So this tuple will be stored in this replay memory. So here we call it, experience playback. So we accumulate the experience with multiple of these tuples. Okay, so here we sample some experience. Use this sampled experience to train this DQN module. The reason of this, we use this sampling because for this sequential experience, it has a correlation between sequential experience. So we know in training of the machine learning models, we don't want that kind of correlation. So we want the data independent from each other, so that we can avoid some divergence of the machine learning model performance. So that's why we use sampling, the sample experience to train the neural network to yield the Q value. So here we have two Q network. The reason we use a 2Q network instead of one, because, so here you can see, remember we have this temporal difference, right? So this part is the target Q value. So this target Q value is generated by this target Q network. So here, this is the Q value generated by this evaluation Q network. If we just use one single Q network to generate both the target Q value and the Q value, so these two Q values could be different. So we use this, if we use one single Q network to generate two different Q values, that will cause some conflict or divergence. So okay, that's why we use two different Q networks to generate two different Q values. So here, for each Q network, you just have an input, the state. So you give a state, they will generate the Q value. So the generated Q value will be used to calculate a loss. Remember this loss, when we introduce Q learning, this is the temporal difference. So this DQN, so we try to train the DQN model to minimize this temporal difference. So to minimize this loss, minimize this difference. So this, if we calculate the gradient of the loss with respect to the Q network parameter theta, so we can update the network parameter. So this is pretty similar to the training process of deep learning network. Okay. So here you can see in this this evaluation Q network, also called a prediction Q network. So basically, it produce this Q value. This Q value here is like the Q value we want to derive from the Q learning, or from the table of the Q learning, right? This is the Q value we want. Here the targeted Q value here. So here we remember in the traditional deep learning network, the target actually is known. Target is fixed. When we, for example, use a convolutional neural network, right, to use some labeled image to train the convolutional neural network, the label is the target. So the label is already known. Label is fixed. But here we want to have Q values. Those Q values are still being updated. So these Q values are not stable value. They are still being updated. So the target, are also changing. So that's another reason we use the two Q network. So the target Q network will be keep fixed for just for a while, for every n updates. So the parameter, like here, this theta manners, will be keep unchanged. So the target Q value will be considered fixed for a while. So every n updates, the parameter theta of this prediction Q network will be sent to the target Q network. So this Q theta will be updated. So temporarily, this target Q network will be considered as fixed. So that the target Q value will be considered fixed. So this will avoid some divergence of the Q network training. Okay, so we evaluated the method of this deep Q learning for cognitive GPR. So we compared from the performance GPR agent using different reward function. So you can see this is you can see the performance with the overall, the combined reward function has the best performance. Also, we have this the average time spent on locating a target interest. So the DQN approach has a better performance than the random approach. The random approach corresponding to the GPR agent just randomly walk in the field, scan in the field. Another approach, also deep reinforcement learning approach, so has a better performance. So we are investigating why this approach has a better performance. Okay, so this is mainly about the result of cognitive GPR. So besides cognitive GPR, we also did some other research. So one aspect is, okay, when we use GPR data to train the deep learning models, right? The ground truth data is scarce. So we propose, okay, how about use some generative model to augment the GPR data. So for machine learning model training. So basically, you can see if you want to get some ground truth GPR data, so it's a very expensive labor sum to collect the data. So you need to have the real, you have the exact knowledge about the pipe material, the burial depth. So we do this kind of experiment to collect the GPR B-scan image, so that you can have the label information for machine learning training. So it's very difficult to get this ground truth training data. So we use this GAN model to train the neural network. So basically, a GAN has a generator module, has a discriminator module, right? So these two modules compete against each other. The generator tries to, generate some GPR data as real as possible to trick the discriminator. So you can see the output from the generator goes to discriminator. The discriminator tries to differentiate between the real data and the generated GPR data. So you can see, this is recursive competition process will result in improved generative performance and discriminative performance. So the improved generative performance will generate, GPR data as real as possible. So the generated GPR data could be used for training some, classifier to, for example, classify unlabeled GPR data. So you can classify, for example, the pipe size, pipe materials, burial depths. So GAN, is very another popular topic. So these images are, generated from a GAN network. So you can see it's a very, very realistic. So one thing is, okay, the input to the generator is random noise. The reason we use random noise because it is very diverse. So it's very diverse. it can be converted to any information. So here, our research, problem is okay. Instead of using random noise as input to this generator, how about we use some simulation information about the GPR scanning process. So basically here we have a GPR Max simulator. So this GPR Max simulator already, solve this kind of physics equation. We call it Maxwell equation, right? The electromagnetic wave propagation in the medium. So it simulates this physics equation, and what about we use the results from a GPR Max simulator as the input to the generator, so to improve the performance of the generator. So maybe this can improve the performance of this GAN model to generate more genuine GPR data. So the idea is we try to have this physics guided GAN model to augment GPR data. So we process the GPR data in temporal domain, spatial frequency domain. So we try to add both domain information in the GAN, so to improve the performance of the GAN. I will skip this part. So this is the generated GPR data. So you can see pretty realistic to real world GPR data. So if we use the generated GPR data to train the classifier, so we can get the improved classification performance. So this orange part means the improved performance of the classification from the generated GPR data. So besides GPR data augmentation, we also did some mapping. So first, at the beginning, we try to use the virtual reality to, for example, to map the underground infrastructure. We embed from the GPR data into the proper location of the scan of underground pipeline. So to indicate this is about the condition of the pipeline at this location, at this scanning location. So when we did this virtual reality based mapping, so it's very time consuming to construct a 3D model of this environment, the street, the building, so very time consuming. So and then we switched to augmented reality. So what about we use the physical view from a camera, the physical view of the environment. So we overlay the physical view of the environment with some virtual object. Like here, the virtual pipeline we reconstructed with some 3D software. So we overlay the physical view with this virtual object. Imagine if we have enough information about this underground pipeline, so we can put them as augmented reality information. Put all this information in the format of this 3D reconstructed pipeline or other visualization format. So here, one of our students, Tucker, and also Evan, so they developed this drone-based visualization, AR-based visualization. So you fly the drone, so it can give you a view of this. So you could mean, this 3D pipeline is about the actual pipeline and the surface of this area. So here, there's some other, products like Microsoft HoloLens. They have this kind of device, wearable device. So it can give you the, for example, the visualization of subsurface pipelines around the person. But the range is very limited. So our research, you can fly the drone, okay, along a city street. So you can get a, as much view as broad view as possible. So it has much more flexibility. Another part of the research we are doing is, okay, we are using LiDAR try to capture the above ground environment. So we are wondering whether we can combine this above ground visualization and subsurface visualization. So to build a digital twin of this urban infrastructure. So this is some experiment we did with collaboration from University of Vermont. Okay, so I think that's my presentation. Everybody is here?
Yeah, thank you, Dr. Wu. Thank you, Dr. Wu. Yeah, now the question time.
Sorry about the presentation is too long, right?
Oh, that's good. Yeah. Anybody has questions? Okay, so.
Doctor, thank you for your presentation, because my background is about biology, so, but I'm very interested with your presentation, like how to do something to facilitate the urban management, or, yeah, I think that's interesting, but I don't have too much question because it's like the background is a kind of gap. So, but thank you.
Yeah, thank you very much for your interest.
Yeah.
Thank you very much. I think it is quite very interesting work. So I think a lot of interesting technologies combined together to solve a real problem. So I think it's good work.
Oh, thank you very much, Dr. Chen, for your encouragement.
Hi, Dr. Wu. First of all, thank you very much for your great presentation. I have a quick question. Probably I missed something. I have a question about your Q learning algorithm. So you say basically you need to use recursive to update the Q value. So I'm just curious when you stop updating the Q value. So is there like a threshold, say like the difference between the new value and the older value reach to a very small number? What is that? Yeah, I just missed that part.
Yeah, you can compare the temporal difference, for example, the older value, the difference between the old value and the new value. So if the difference is very small, less than threshold, so it can stop.
Oh, okay. Yeah, that's what I'm. Okay, so you use the threshold. Okay. Yeah, that's what. Okay. Yeah, got you. Yeah, it's right here. So yeah. Okay.
Just to add on that answer is that the way the reinforcement learning architecture works is that it learns from experience. So as it's moving around, it's trying to gather as much information about the environment. And while it is doing that, it tries to maximize the action that will give it the best reward for the next move. So it's a cumulative discounted reward that it gets at the end of the day. So the way you learn any any way of doing something. So the way the reinforcement agent will work is that it moves around, collecting information, and out of that information, it either get a penalty or a reward. And based off of that, the Q value will be the quality of the previous action. How good was it that it got a reward? So it works towards getting a better action every other time. So if the I think you saw a dinosaur there. So if it starts at any other time at any spot of the maze, it will know what would be the best action to take from that state that it's starting from. So by the time it learns all the experiences in that environment, that's exactly the point where you stop from. So is that point where you reach like an optimum policy that it learns how to navigate in that environment, that an action that will be taken will be the best action towards getting the goal, or in this case, identifying the pipe.
Yeah, any other questions? Okay, so Dr. Wu, what do you think?
I think people, they may
Need some time to
higher.
digest the GPR and yeah, reinforced learning, but it's good. Yeah, I see. Yeah, if anybody just the maybe someone your field is not like the GPR or something, but the technique that will cover like the reinforced learning, data augmentation, all this thing can be applied to a lot of applications. So if you are interested in this technique, yeah, we can just work together to how to customize Wu's method, okay, in your applications.
Mm-hmm.
Yeah, because the fundamental technique is basically the same. We talk a lot about this one, but forget about the GPR. I think the Q learning and all those kind of this technique is still useful. Yeah. So if we have a question, yeah, go ahead. Sorry about that.
Yeah, Dr. Liang is totally correct. So the methodology, for example, data augmentation, whether you work on medical data or any other data, right? Temporal domain, frequency domain. So the technology data augmentation is still useful. If you have, for example, limited ground truth data. Also, this reinforcement learning, it's very powerful to generate for this kind of a sequential decision-making problem. So I was wondering, anyone doing research involve reinforcement learning or deep reinforcement learning. So we can always discuss.
And again, right? And VR and AR. So this project involves a lot of technical ingredients. So
yeah, too many ingredients. That's why we got this super long presentation.
It's good. Yeah, we don't want to hide anything. We just want to show, so all the possible, there's a potential opportunities that we can work together to do something. Okay, I think, Dr. how about we stop here?
Sure.
Okay, thank you everybody. Thank you for showing up. I think it's good. We are thinking about still the workshop 5. We have not decided yet, but if we have it, we are focused on the Python programming for data science. We are still coordinated with the speakers. So if we did, I'm going to send an email to you. And don't forget, don't forget to evaluate the course. I'm going to post today's talk on the YouTube, and you guys can go ahead to just do some evaluation. Yeah. Okay.
Okay. Thank you very much. Thank
Dr.
you.
Lee, do you have something to do you have something to add?
No, I'm fine.
You're fine. Tired? Okay. Okay. I will see you guys just hopefully yeah, thank you, Dr. Wu. Thank you.
Sure.
Yeah,
Thank
thank you for the patience. Yeah.
Thank you.
Okay.
Yeah.
Thank you for your time.
Yeah. Okay. Bye.
Bye. Bye.